Hello everyone and welcome to A+ Physics. I'm Dan Fullerton, and in today's video we're going to take a look at the 2016 AP Physics-C Electricity and Magnetism free response questions. This exam was just given recently. They have not yet released the scoring guide, so odds are pretty high that I may miss a point or two, but hopefully this will get you a good feel for the questions at least. So as we get started, I would note, it looks to me like questions 1 and 2 were pretty straightforward, with question 3 being by far the more challenging question. So hopefully as you look over these, if you took the exam, 1 and 2 should look pretty familiar, and if you struggled on 3, I bet you're probably not going to be the only person who struggled on 3. So with that, let's dive in and take a look at E&M number 1. All right, for number 1, we've got 2 point charges, Q1 and Q2, fixed in place on the x-axis at positions x is -1 and x2 is 0.5 meters. Q2 has a value of 2 nanocoulombs. Values of electric potential are illustrated by the equipotential lines, and it asks us to calculate the value of Q1. Well, to do that, I would recognize that electric potential, our voltage there, is going to be the sum of KQ over R. And if we use the point where we know that the potential at 1.5, 0, 1.5 on the x-axis is equal to 0, we can then write that KQ1 over its distance from our point, 2.5, plus KQ2 over its distance, 1, equals 0. Now it just becomes an exercise in algebra. This then implies that KQ1 over 2.5 equals -2 nanocoulombs times K over 1, which implies then that Q1 must equal 2.5 times -2 nanocoulombs over 1, or -5 nanocoulombs. Fairly straightforward there. Now for B, we're asked to draw a vector representing the direction of the electric field at point C on the diagram. And if you look, you see C toward the y-axis, toward the top, just to the left of the y-axis. The direction of the electric field there would be, well, it goes from high to low potential. So you've got the -12 volt equipotential, the -16 volt equipotential. Starting at C, I would draw a vector toward the -16 volt potential, recognizing that it crosses all equipotentials at right angles at 90 degrees. So 90 degrees perpendicular to the equipotential at C, draw it toward the -16 volt equipotential. All right. Calculate the approximate magnitude of the electric field strength at point D on the diagram. Well, if we're doing that, I would approximate this as the potential divided by the distance, which would be 4 volts over 0.2 meters, or about 20 volts per meter. D, the equipotential labeled 0 volts is the cross-section of a nearly spherical surface. Okay. Calculate the electric flux for this surface. Okay, as we look at D then, the flux, electric flux, is going to be charge enclosed divided by epsilon naught. Thinking back to Gauss's law, this came up a lot as we were going through that subject. Our enclosed charge is 2 nanocoulombs. Epsilon naught, 8.854, times 10 to the -12 Newton meters squared per coulomb squared. Just a little bit of calculator work to come up with about 226 Newton meters squared per coulomb squared. All right, now we get into part E. We're going to place a proton at point A and then release it from rest. Find the work done by the electric field on the proton as it moves from A to E, and then find the speed of the proton when it reaches point E. And as I do this, the first thing I'm going to do is recognize that the work done is going to be the change in potential, so that'll allow us to calculate the work done. And then to find its speed, well, I recognize that the work done is going to be the change in the proton's kinetic energy, so we can solve it that way. 2 fairly common things we've been doing throughout the course. So, looking at E part 1, work is charge times our change in potential, or our potential difference, which is 1.6 times 10 to the minus 19 coulombs, the charge on our proton, times our difference in potentials, 8 volts, or 1.28 times 10 to the minus 18 joules. And for part E2, find its speed, while recognizing that work is the change in kinetic energy, the work energy theorem. This implies then that our work, 1.28 times 10 to the negative 19 joules, must be equal to 1/2 times the mass of our electron times our speed squared. Mass of our electron, mass of our proton times speed squared, which implies then that our speed is the square root of 2 times our kinetic energy divided by our mass, which is 2 times 1.28 times 10 to the minus 19 joules, divided by the mass of our proton, about 1.67 times 10 to the minus 27 kilograms. Square root all of that, and I come up with about 39,200 meters per second. And that brings us to F, the last part of the question. Now we release an electron from rest at point B. Which of the following indicates the direction of the initial acceleration, if any, of the electron? Well, I would choose left here. A negative charge feels a force opposite the direction of the electric field, and the electric field runs from high to low potential to the right, so the electron's going to feel a net force to the left. Therefore, it's going to accelerate to the left. So a couple sentences around that, but the key answer is to the left. All right, that should answer number 1. We'll take a quick break and be right back with question number 2. All right, and we're back with question number 2, a circuits question. The circuit shown has a source of variable EMF, that's script E, an ideal ammeter A, an ideal voltmeter, a resistor, and a sample of wire with resistance R. How does the current through the wire sample compare with the current through the resistor R for part A? Well, 2A, that's gotta be the same. What we have is a series circuit. We've got no current flow through the ideal voltmeter, and R and little r are in series, so they have equal current flow. Then for part B, how does the potential difference across the wire sample compare with the potential difference across the resistor R? That's going to depend on the resistance of the sample. The larger resistance will experience a greater potential difference consistent with Ohm's law. So the key here is understanding our potential drop across an element in the circuit is the current through it times its resistance. So depending on what R is, what little r is compared to big R, is really going to determine the answer to that one. All right, part C. With the sample of wire in place, the EMF of the source is set to a given value. The current through the potential difference and the potential difference across the resistor, capital R, are measured. This is repeated for several values of EMF, and the data are recorded, and it gives you a nice little happy data table. Indicate which values, which quantities should be graphed to yield a straight line that could be used to calculate a numerical value for the resistance of the wire sample. All right, so for part C, what I would want to graph if I were trying to calculate the resistance of that wire sample, I'd recognize that little r is going to be the potential difference across little r divided by the current through little r. Well, the voltage across little r, the potential difference across little r, is just going to be your EMF minus the potential difference across big R using the loop rule, Kirchhoff's voltage law. And the current through little r is going to be the same as the current through big R. So we already have that quantity right there. So that's what I would want to be graphing. So what do I need to add to my plot? Well, first off, I would say this goes on our vertical axis. There's our horizontal. And I'd add a column for E minus VR to the data table, and when I do that, I come up with the values going down 0.071, 0.165, 0.23, and 0.33. And that, I think, would get you to where you need to go. Now, for D, on the graph on the grid below, plot the straight line data points from part C. Clearly scale and label all axes, including units if appropriate. Draw a straight line that best represents the data. All right, well, let's see what we can do here. I've got my grid. What I would want to graph then, I've got E minus VR on the vertical. So E minus VR, units are volts. I've got my current through capital R on the X on the horizontal. That's going to be in amps. And I'd make a scale something like 0.2, 0.4, 0.6, 0.8, 1. And for the Y, we could go, say, 0.08, 0.16, 0.24, 0.32, and 0.4 volts. Then all we have to do is plot our points. Looks like we've got an IR of 0.162 versus a Y of 0.071. So that's going to be somewhere around there. I'm going to plot these pretty quickly so you don't have to watch all of this. 0.165 and just 0.327 and 0.165. That's going to put us right around here. Yeah, somewhere around there for another point. We've got 0.49 and 0.23. So that's going to be somewhere right in here. And one more point, we've got 0.687 and 0.33, which is going to put us right up around there. Something kind of like that. And that should get us going pretty well there. Then it's going to ask us to draw a line. Draw our line. Best fit line looking something like that, and then we'll take a couple points on it to find the slope. And it looks like 0, 0 runs through my graph, so that's an easy one. And I've also got a nice point there to take the slope from. So R is going to be equal to the slope, which is rise over run, which in this case is going to be 0.288 volts, my rise, divided by my run of about 0.6 amps. And I come up with R equal to 0.48 ohms. Make sure that decimal's easy to see. So that gets us through part D. All right, E, use your straight line to calculate the value of the resistance. Oh, pardon me, we just did part E. Let's call that E. And then F, the wire sample has a length of 3 meters and a radius of 1 times 10 to the minus 3 meters. Find the resistivity of the material from which the wire sample was made. All right, I'm going to get ourselves a little bit more room here. What we know is our length equals 3 meters. R is 1 times 10 to the minus 3 meters, our radius. And the resistance of this is 0.48 ohms. All right, I can use resistance of a cylindrical conductor equals rho resistivity times length divided by the cross-sectional area. This implies then that our resistivity must be RA over L, or 0.48 ohms times our area, pi r squared, pi times 10 to the minus 3 meters squared, all divided by our length of 3 meters. Put that into my calculator, and I come up with a resistivity of about 5.03 times 10 to the minus 7 ohm meters. And I think that should work pretty well for that question. G. Suppose the ammeter used to collect these data was not ideal. Would the actual value of the resistance of the wire sample be greater than, less than, or equal to that calculated in part E? Well, if the ammeter has some resistance, the voltage drop across the sample would be less than the EMF minus the voltage across resistor capital R, so the slope would be less. So the actual resistance would be less than what we calculated previously in part E. So that's G1, and make sure you have some words justifying your answer. And for G2, now we're asked if the ideal voltmeter is replaced by a voltmeter that is not ideal and the experiment is repeated, would the readings of the ideal ammeter be greater than, less than, or equal to those in the data chart before part C? Well, if the voltmeter is non-ideal, the overall resistance of the circuit decreases since capital R and the voltmeter are in parallel. If the overall resistance drops, the current through the ammeter increases, so I would say this is greater than. And make sure to write down a sentence or two justifying that answer. And that's it for number 2. We'll take a quick break and come back with the doozy, number 3. And we're back with number 3. Problem pretty straightforward from a physics perspective. However, this one has a bit more math involved, a bit more calculus, as we've got to solve a differential equation. And that's where I'm expecting we're going to see most students get hung up on the free response question. But very fair question, something we should be able to do. So let's dive in. We've got a conducting bar of mass m, length L, and negligible, no resistance, connected to 2 long vertical conducting rails of negligible resistance. The rails are connected by a resistor at the top. The entire apparatus is in a magnetic field of magnitude B going into the page. The bar is released from rest and slides without friction down the rails. What's the direction of the current in the resistor? And to my mind, that's a Lenz's law problem, a right-hand rule sort of problem. As the bar is sliding down, the amount of flux into the plane of the page is increasing. Therefore, you're going to induce a current that is going to want to oppose that. So the direction of the current in the resistor, if you're going to have this turning counterclockwise through that loop of conductor in order to satisfy Lenz's law, through the resistor at the top, that's going to be to the left. So I would answer to the left, and I would put some sort of explanation, making sure to mention Lenz's law in there as you walk through how that occurs. Notice it only says you need to tell the direction. Even though it doesn't have any points for the explanation, it usually helps me to write that out briefly, just so I can make sure I didn't make any mistakes as I walk through the logic. For 3b, we're now asked, is the magnitude of the net magnetic field above the bar at point C greater than, less than, or equal to the magnitude of the net magnetic field before the bar is released? Well, for part B1, that's going to be less than. As the bar is dropped, the induced current creates a magnetic field that opposes the external field. While the bar is above point D, is the magnitude of the net magnetic field at point D greater than, less than, or equal to the magnitude of the net magnetic field before the bar is released? Well, for B2, this one's going to be greater than. As the bar is dropped, the induced current creates a magnetic field which adds to the external magnetic field. So for B2, we're going to have greater than. And both of these have to do with Lenz's law and looking at directions of induced currents and induced fields and things like that. All right. For parts C and D, we're supposed to express our answers in terms of M, L, R, B, and appropriate physical constants. So let's take a look, and we'll start with C, keeping those rules in mind. Write, but do not solve, a differential equation that could be used to determine the velocity of the falling bar as a function of time t. Now, I always start these with the free body diagram. We've got a magnetic force pointing up, and we've got the weight of the bar down. So using Newton's second law in the y direction, net force in the y direction, which is our mass times acceleration in the y direction, that's going to be mg minus our magnetic force. ma is going to be our mass, capital M, and acceleration in the y is the derivative of velocity with respect to time. Therefore, I could write, since the magnetic force is equal to ILB, one of those formulas we should really know by now, and our current is our EMF divided by our resistance, LB, then E must be BL times our velocity. Therefore, mg minus, we'll replace our magnetic force with B squared, L squared, V divided by R, must all be equal to m dV dt. And if I separate this in one more step, I could then write that dV dt equals G minus B squared L squared V over capital MR. And there I've got a differential equation in terms of velocity and the derivative of velocity. Now for D, determine an expression for the terminal velocity, Vt of the bar. Well, Vt occurs in a very specific circumstance. That happens when we have no more acceleration, when the magnetic force equals the weight of the object. So if I start with our magnetic force equal to mg, that occurs when g equals b squared L squared V terminal, all divided by mr. Therefore, just solving for Vt, our terminal velocity is g capital M capital R divided by b squared L squared. That's almost easier than part C. All right, now for E and F, we're going to express our answers in terms of Vt, ml, rb, and physical constants as appropriate. Okay, so as we do this, let me go to another page to give ourselves a little bit more room here. Now we get into it. E, derive an expression for the power dissipated in the resistor when the bar is falling at terminal velocity. So for E, power, slid up for some reason, power equals V squared over R, which is going to be B squared L squared Vt squared over R. Really just plugging into our power formula with what we know. And then F, everybody's favorite part. Using your differential equation from part C, derive an expression for the speed of the falling bar Vt as a function of time t. Okay, as we do this, we start off with our differential equation, dv dt equals g minus b squared L squared V divided by capital Mr. This implies then that dv over dt equals gmr over mr minus b squared L squared V over mr. Trying to get to a common denominator. What I really want to do is get all my variables of v on the same side, separate my variables, and t, anything is a function of time, on the other side. So therefore, dv dt equals gmr minus b squared L squared V all over mr. I can pull the v over into the denominator on this side, the dt over into the numerator on that side, some cross multiplication, so that dv divided by g capital M capital R minus b squared L squared V must be equal to 1 over mr dt. I have all my variables of v on the left, everything in terms of t on the right. Now I can integrate. If I integrate both sides, I'll integrate the left-hand side from 0 to some velocity v of dv over g capital M capital R minus b squared L squared V. The right-hand side, the corresponding integration in terms of t, is from time 0 to some final time t of 1 over mr dt. All right, to integrate this further, on the left-hand side, we've got dv over v, but I've got this minus b squared L squared in front of the v that I've got to take care of so that I can get this in the form du over u. So what I'm going to do is I'm going to write this on the left-hand side as minus 1 over b squared L squared, integral from 0 to v, of minus b squared L squared dv over gmr minus b squared L squared V. Now this is in the form du over u, so I'm going to be able to integrate that with the natural log function. And that's going to be equal to, on the right-hand side, integral of 1 over mr dt. Well, 1 over mr is a constant. That comes out. And the integral of dt is just t, evaluated from 0 to t, is again going to be t. So the right-hand side becomes t over capital M capital R. All right, this implies then, since we know the formula, the integral of du over u is the natural log of u, plus our constant of integration. This allows us to write on the left-hand side that we end up with the natural log of G capital M capital R minus B squared L squared V evaluated from 0 to V. And that must be equal to, well, if I multiply the negative B squared L squared through to the right side, I get minus B squared L squared T over MR. All right, let's see if we can't take that, and we'll slide down a little bit and go from there. Okay, so now we need to do something over here with this piece. We've got to evaluate it from 0 to V. So this implies then that the log, natural log, of G capital M capital R minus B squared L squared V, when we evaluate it at V, minus all of this when we plug in 0 for V, which will be minus the log of G capital M capital R, equals our right-hand side minus B squared L squared T over MR. All right, which implies then, well, the log of a difference is the quotient of the logs, excuse me. So that will be, left-hand side becomes natural log of G capital M capital R minus B squared L squared V, all divided by G capital M capital R. And that is still equal to minus B squared L squared T over MR. All right, I'm going to go to another page for our next part here, give ourselves a little more room. So this implies then, well, let me make sure I know where we're at. This implies then that G capital M capital R minus B squared L squared V over G capital M capital R is equal to E, oops, sliding up again, is equal to E raised to the minus B squared L squared T over MR, as I raise both sides e to that power. So now I'm going to try and get the V all by itself. It becomes mostly an exercise in algebra. So if I multiply both sides by GMR, on the left-hand side I have G capital M capital R minus B squared L squared V. Right-hand side becomes G capital M capital R e to the minus B squared L squared T over MR. All right. We've got this B squared L squared V. That's the term I want by itself. So if I add that term to the right and subtract this term, we'll get that on the left. I come up with something right around, let's see here, B squared L squared V equals G capital M capital R minus G capital M capital R times E raised to the negative B squared L squared T over MR. GMR, GMR, I can factor that out. Just write that V equals, well, we've got G capital M capital R times the quantity 1 minus negative B squared L squared T, oh, excuse me, I forgot an important part there, 1 minus E raised to the negative B squared L squared T over capital MR. And we have to take care of this B squared L squared divided by B squared L squared. So GMR over B squared L squared times the quantity 1 minus E to the negative B squared L squared T over MR. All right, and I'm supposed to answer in terms of physical constants and ML, R, and B. So I've got ML, R, and B, and physical constants G, E, things like that. So I think I'm in good shape there. But note, if I wanted to take it a step further, I could also recognize that the terminal velocity is GMR over B squared L squared. So I could write this if I wanted to, which implies then, if we recall that, our terminal velocity equals G capital M capital R over B squared L squared. which implies then that V equals Vt times the quantity 1 minus e to the b squared L squared over mr, 1 minus e to the negative b squared L squared over mr t. So you could write it that way as well. And that, I think, gets you in pretty good shape for question 3F. All right, hopefully that gave you a good feel for how you might go about attacking these sorts of questions. The links to the questions themselves are down below the video. Thank you so much for your time, everyone, and make it a great day.